Devendra Singh. I am teaching you solution, dilute solution and colligative properties. Topic Thermodynamics derivation of a relationship between elevation in boiling point and molecular weight of a non-volatile solute. Figure gives the vapor pressure temperature curves for the solvent and the solution. The horizontal dotted lines down corresponding the external pressure cuts the solvent and the solution curves at the point E and F, which correspond to temperature T0 and Ts respectively. Thus, by definition, T0 is the boiling point of pure solvent and Ts is that of solution. Obviously, Ts greater than T0. The increase Ts minus T0 is called the elevation in the boiling point and is usually represented by delta Tb. Thus, delta Tb is equal to Ts minus T0. Equation number first. The relationship between the elevation in boiling point and the concentration of the solution can be obtained by Clausius-Clapeyron equation and Raoult's law to the. On page number first, figure is given vapor pressure and temperature. AB shows curve solvent and CD curves shows solution, which cuts the point F and G and E, and temperature is shown in the x-axis Ts, T0. Ts minus T0 is equal to delta Tb, and vapor pressure of the solution is decreases Ps, and vapor pressure of the atmosphere P0 is given in the figure on page number first. On page number 2, different conditions shown in figure. Clausius-Clapeyron equation, which is applicable to a phase equilibrium in the integrated form, is given by log P2 divided by P1 is equal to delta H upon R, bracket 1 upon T1 minus 1 upon T2, bracket close, where P1 is the vapor pressure of temperature T1, P2 is the vapor pressure of temperature T2, and delta H is the molar latent heat of transition. Point G and H lie on the same solution curve. Suppose the vapor pressure of the pure solvent and the solution at temperature T0 are P0 and Ps respectively. Then from we have A corresponding to point G, temperature is equal to T0, vapor pressure is equal to Ps. B corresponding to point F, temperature is equal to Ts, vapor pressure is equal to P0. Hence the equilibrium solution reversible vapor, according to the Clausius-Clapeyron equation, we have for the point G and H, log P0 divided by Ps is equal to delta HV upon R, bracket 1 upon T0 minus 1 upon Ts, equation number 2, where delta HV is the latent heat of vaporization of 1 mole of the solvent from the solution. When the solution is dilute, delta HV is nearly equal to the latent heat of evaporation of the pure solvent on page number 2. On page number 3, equation second can be written as log P0 divided by Ps is equal to delta HV upon R, bracket में Ts minus T0 divided by T0 Ts, bracket close, or log P0 upon Ps is equal to delta HV upon R into delta Tb upon T0 Ts, bracket में Ts minus T0 is equal to delta Tb, equation number 3. Further, when the solution is dilute, Ts is nearly equal to T0. Hence, equilibrium equation number 3 can be written as log P0 divided by Ps is equal to delta HV upon R into delta Tb upon T0 का square, equation number 4. According to the Raoult's law, we have P0 minus Ps divided by P0 is equal to X2, equation number 5, where X2 is the mole fraction of the solute in the equation. Equation 5 can be written as 1 minus Ps divided by P0 is equal to X2, or Ps upon P0 is equal to 1 minus X2, taking log on both the sides. Log Ps are divided by P0 is equal to log 1 minus X2, ब्रैकेट में लिखना है log Ps upon P0 और is equal to minus log bracket में 1 minus x2 equation number 6. Since x2 is very small, less than 1, the expansion of log 1 minus x2 as the infinite series is given by on page number 3. On page number 4, log bracket में 1 minus x2 is equal to minus x2 minus 1 by 2 x2 square minus 1 by 3 x2 का cube and so on. Neglecting x2 square comma x2 cube etc. as x1 is much smaller than 1, we have log 1 minus x2 nearly equal to minus x2 equation number 7, or log 1 minus x2 equal to minus x2. From equation 6 and 7, log ps upon p0 is equal to x2 equation number 8. Substituting these values in equation 4, x2 is equal to delta hv into delta tb divided by r into t0 square equation number 9, or delta tb is equal to rt0 का whole square x2 upon delta hv equation number 10. However, the common practice in the studies on elevation in boiling point is not to express the concentration in terms of mole fraction but in terms of moles of solute per 1000 gram of the solvent, that is in terms of molarity small m. Hence, equation 10 is further modified as follows. If n2 moles of solute are dissolved in n1 moles of solvent, the mole fraction of the solute bracket x2 in the solution will be given by x2 is equal to n2 divided by n1 plus n2, as the solution is supposed to be dilute n2 less than n1, so that the denominator n2 on page number 4. On page number 5, can be neglecting the comparison to n1. Hence, for the dilute solution, above equation can be written as x2 divided is equal to n2 upon n1. Further, if W2 gram of the solute is dissolved in W1 gram of the solvent, and M2 and M1 are the molecular weight of the solute and solvent respectively, then N2 is equal to W2 upon M1 and N1 is equal to W1 upon M2. So, hence, x2 is equal to N2 upon N1, W2 upon M2 divided by W1 upon M1 is equal to W2 upon W1 into M1 upon M2. Putting these values of x2 in equation 10, we get delta TB RT0 the whole squared upon delta HV into W2 upon W1 into M1 upon N2. Delta TB is equal to RT0 square upon delta HV divided by M1 into W2 upon W1 M2. Equation number 11. Putting delta HV upon M2 is equal to LV, latent heat of vaporization per gram of the solvent. Equation 11 becomes delta TB RT0 square upon LV into W2 upon W1 M into M2. Equation number 12. Let us say molarity of the solution M. Thus, M moles of solute are dissolved. On page number 6, putting these values in equation 12, we get delta TB is equal to RT0 square upon LV into small m upon 1000. Equation 13. Or delta TB is equal to RT0 square upon 1000 into LV into small m is equation number 14. For a given solvent, the quantity RT0 square upon 1000 into LV is a constant quantity because LV, 2, T0 and R the constant. It is represented by Kb and is called molar elevation constant or Elisho-Koppel constant. That is Kb is equal to RT0 whole square divided by 1000 into LV, equation number 15. Hence, equation 16 can be written as delta TB is equal to Kb into small m. If small m is equal to 1, delta TB is equal to Kb. Equation number 16. The molar elevation constant may be defined as the elevation in the boiling point when the molarity is unity. On page number 6. The PDF is given on page 1 to 6 of the thermodynamics derivation of a relationship between elevation in boiling point and molecular weight of a non-volatile solute.